Director of the Institute of Engineering at UNAM. So very welcome to this session. This session was named a session on green technology. We're going to have three speakers. Two of them are going to talk about robotic-related topics, and the other will talk about energy management in computers. So I'm going to read the summaries of the CVs of the three presenters in order for you to know who is presenting. So the first presenter is Yamasaki Yoshiaki. He received his BS, MS, and doctoral engineering degrees in mechanical engineering in 1984, 1986, and 1998 from Waseda University. From 1986 to 1995, he was a researcher at the Mechanical Engineering Department of the Central Research Laboratory at Mitsubishi Electric Corporation, and from 1995 to 2004. He was a researcher at the Mechatronics Engineering Department, Advanced Technology Research and Development Center, also at Mitsubishi Electric Corporation. He came to Meisei University in 2004 and is currently professor in mechanical engineering in the Department of Interdisciplinary Science and Engineering and the School of Science and Engineering. Since 2017, he is an executive board member of the Japan Design Engineering Society. His interests include remote control rescue robots, autonomous rescue robots, autonomous mobile robots, simultaneous localization and mapping, robot operation systems, interface between humans and robots, manipulators for discovering victims, sensor systems for human body detection, general mechatronics equipment, and space elevators. The second presenter is Yasutaka Wada, who is an associate professor of the Department of Information Science, also at Meisei University in Tokyo, Japan. Before joining Meisei University in 2015, he was an assistant professor at Waseda University in Tokyo, Japan, an assistant professor at University of Electrocommunications in Tokyo, Japan, a junior researcher at Waseda University, and a research associate at the same university. He was also an associate professor at Egypt, Japan, University of Science and Technology in Alexandria, Egypt from 2010 to 2012. He received his BS, MS degrees in electrical engineering and his PhD degree in computer science from Waseda University. So both of them have like the same background and work in the same university. He has served as a program committee vice chair of the IEEE Cool Chips Conference series since 2015. His research interests include parallel processing and applications, green computing, heterogeneous computing, automatic parallelizing, compilers, and multi-core, many-core processors architecture. His research and development activities cover various systems from embedded systems to high-performance computer environments to realize high-performance, energy-efficient, and easy-to-use computer systems. He's a member of ACM and the IEEE Society and Computer Society and other two institutes. Finally, Noé Velázquez, he's a full-time professor researcher at the Irrigation Department at Chapingo Autonomous University and a part of the basic academic core of the graduate program in agricultural engineering and integral use of water. He's a member of the SNI, National Researcher Systems of Mexico, and graduated as a mechanical agriculture engineer in Chapingo Autonomous University. He got a master in agricultural engineering with a specialization in computer vision from 2008 to 2010, and a PhD in agricultural engineering with a specialization in farm robotics from 2010 to 2013 by Tokyo University of Agriculture. His research areas are automation and robotics and agriculture, and he teaches courses on robotics, instrumentation, sensors, differential equations, physics and statistics, and probability. He has work experience as a researcher in an IFAP, in agricultural mechanization program from 2013 to 2014, and he is the creator of the first farm robot at Chapingo Autonomous University and the leader of the first Mexican team that participated in the field robot event in 2017 that was held in England in 2017 and in Germany in 2018. So we will begin with Professor Yoshihachi Yamasaki, who will present development of rescue robots at Messi State University.
Okay. Thank you very much, kind introduction. Now I would like to start the presentation of the title is Development of Research Rescue Robots at Messi University. My name is Yoshihachi Yamasaki, and I come from Japan. This figure shows the disaster of the earthquake. The table one shows the major earthquake that occurred in Japan and Mexico in recent years. Thank you. Number one, September 6, 2080, Hokkaido earthquake was occurred this year. And green line, last year, Mexico City earthquake was occurred. Magnitude is 7.1. Dead person is up over the 133. This is Mexico City earthquake photos. Very, very sad things that it is. And the collapsed houses over the 11,000. In Japan, blue line, the Great East Japan earthquake was occurred in 2011. This great disaster was a lot of person was died by tsunami. This is Japan map. The tsunami was occurred number 4 the area. And the rescue robot, the important earthquake is the Great Hansen earthquake that occurred in 1995. In this case, a lot of collapsed houses under the building and house. Many people were died under the houses. Recently, in Japan, attention has been drawn to the development of rescue robots. This figure shows the RoboCup Japan. It is the competition of the rescue robot. And this is the impact. That is a very big project in Japan. Aerial robots, cloud robots, leg robots, animal cyborg, computed robots, a lot of rescue robot was developed now. And human type and snake type. A lot of type of rescue robot is popular in Japan. This movie shows the competitive rescue robot at the RoboCup Japan Open 2017. Okay, next please. In this competition, we have problem of remote control type rescue robots. I'm sorry. The bandwidth of the wireless LAN is limited. If we operate with the web cameras at real time, it is very big data is needed to communication using wireless LAN. And then only a few robots can be moved at the same time. We think how to solve the above problem. In the future, research and development of autonomous rescue robot is necessary. And then today's topic for autonomous rescue robots. 4 topics I explained. First one is the basic research on driving performance of obstacles by autonomous rescue robots. This figure shows the configuration. I'm sorry. Configuration of the rescue Mark IV robot. That was sensors. That have sensors. IMU, that is measured tilt angles of the robot. And 3D scanning system that measures the distance from the obstacles. This is a 3D scan system, and this is a scanning sensor. I'm sorry. Okay. I'm sorry. Oh, two out. Just more please. I'm sorry. Thank you. Oh.
No. It's completely, I don't know what happened.
Okay. I'm sorry. Thank you. And this figure shows the definition of the X, Y, and Z and rotation. And this algorithm shows the autonomous climbing algorithms that was using 3D scanner and IMU sensor. This movie shows the basic research on driving performance of obstacles by autonomous rescue robots. In this case, we use the IMU, but in this case, without IMU control. First, 3D scanner measuring the slopes, and then decides the slopes angles. Next step, this is measuring 3D data. Next step, climb the slope. But in this case, we not use the IMU. Close a sweep, and then turn to the left, and finally drop from the slope. And then we try to IMU control, automatically compensate the direction. He is my student. He held the computer, but not operate. Autonomically compensate the direction to climb the slope. Okay. And this is the result of the, this experiment result. Next, we try to from the top of the stairs and to down. In this case, autonomically is very difficult. And this case is, this movie shows the autonomous moving, including down the stairs. This is 20 times quickly. Autonomous moving using the 3D scanner and measure from the top to the downstairs and the form of the legs. And this is real-time data. Okay. And this is a result of the autonomous slope down. And this measuring data is so good. And I shows the second topics. This figure shows a manipulator that developed in Meisei University. The title is Automation of Searching in Debris by the Manipulator, Searching for Victims, and Experimental Evolution of Distance Sensor for Estimating Search Target Position. Okay. After the earthquake, if we use the rescue robot, but inside the surface damaged building, that is such cases, only camera, it is impossible to look inside the debris. If victim inside the debris, it is necessary to use the manipulator. In this case, rescue robot and control PC was used a wireless LAN control. And this is a simple example of the whole of the box. The problem is we cannot recognize the depth, only two-dimensional data visualization. It is difficult to manually insert quickly, very difficult. An example of a solution, we proposed a measure with a distance sensor, automatic insert operation. This figure is the 3 degree of degree of freedom manipulator. Weight is 1.38 kilograms, very light manipulators. And the head of the sensors, thermography is like this, can measure the temperature. And the sensor unit is only 36 grams. And with the distance sensor is 4, 1, 2, 3, 4. And then it is the scene of the examination of the scanning the holes. In this case, about 22 seconds, it is possible to search the holes. And this is the result of the measured data. We can see the hole. And next step, we try to autonomically insert the heads. In this case, distance sensor looking for the surface and autonomically finding the hole and insert the head and try to the victims. Topic 3, I show this robot, autonomous rescue robot using piezoelectric infrared sensors. That is the background is here. Much victim is here. Control room is only one. And greater escape houses clasp victim buried in lava. Rescue by human is only 2, and it is impossible to all rescue. And then we propose to use the rescue robot to find victim. Second map sends the map data and the location of the victim. It is possible to rescue using these data. Too many persons was rescued. This is an outline of the rescue robot. And this is a thermal image. Here is the most hot spots. But it is difficult to analyze only these data. We propose the piezoelectric infrared sensor detect wide range at once. For a more quick find, we try. And this is a heater. This is autonomous robot for using piezoelectric infrared sensors. And this is a spec of the infrared sensors that is widely 5.1 and 3.6 areas at once, looking for the person. First, we try to the maze like this, and attach the heat source, and looking for the using this autonomous robot. And the result is here. First graph shows the sensor output. Number 1 from 4, that is heat source. In this figure shows the red dot is a map data, and the blue line shows the move log. Result is detect A heat source, and detect A source again, and detect B source. And this case is me. My I explain at here, and robot find me. This is the algorithm of the autonomous finding algorithm. This is piezoelectric sensor threshold, and this is the thermal sensor was applied. And this movie shows the victim discovery experience. Autonomous moving the robot, and under the desk, my student is, he is the victim. Now finding. This figure shows the, and then result I show you. Time rest is short. we detect victims 17 seconds earlier than the only thermal camera. That's the result. And number 4 topics, we try to using mechanical learning, in this case using CNN, by distinguish the door knob. This movie shows the World Cup Japan Open 2018 this year. This is the meta and balance. In this case, confirmation of scale of pressure. And then also the valve at sorry, present value above a certain level. We try to use AI in this case. This is developed and this is an algorithm. And this is using loss moving autonomically. Operator use the simulator and real robot move like this. Very easy. And this shows the doorknob and Japanese style door. That is fusuma. Sliding, it is sliding. And this type is pulling. We try to distinguish these doorknobs by using this CNN. And the public library used TensorFlow and the NumPy OpenCV was applied. And this is algorithm of CNN. A very simple algorithms applied. And this photo shows the learning image of prepared doors knob. This case is 797 photos was used. And this is the learning results obtained using image. In this case, about 552 epochs. That accuracy over the 99%. And this movie shows the real-time recognized by using a machine learning result. This number shows the accuracy. All data over the 90%. And distinguish A, B, C, D query. This is the data over the result. But in this case, number B and number C fusuma is very similar. But all recognition rate more than 90%. Conclusion of this, today's topics. The autonomous of rescue robots and artificial intelligence will become indispensable in the future. Still, we are located at the beginning of the study. And last page shows that this is World Robot Summit in Japan. Date is October 17 and 21, 2018. Venue is Tokyo Big Site. This figure shows the disaster robot category that start again October 17. Okay. And team is 19 team was attend. A Mesa University rescue team was attend. And from Mexico, okay. University Technological de la Mexico. Yeah. And then after tomorrow, I back to Japan and attend this World Robot Summit. Thank you so much for your kind attention.
Okay. Now we go to presentation. We hope it's not flicking now, but I'm sorry about the flicking, but clicking again. Come on. It's please.
Hey, thank you very much. I'm Yasakawada from Meisei University, and today I'm talking about my research, especially focusing on green computing aspect of my research. So actually, I'm researching on how to make the computer system faster and how to make it more useful and how to make it more green. So now today I'm talking about how to make it green. First of all, I'd like to thank for my research collaborator. So today's my talk include many work with my research collaborators. So I'd like to thank all of them. And also I would like to thank for my students attending this research. Anyway, so my research background and my goal of my research is to realize the high performance and easy to use computer system. And also we would like to reduce the power consumption of the system because we still have many higher demand for the performance of the computer system. And also we need to realize much more higher, longer battery life or sustainability of the society or cities. So we need to realize making the computer system faster and also while reducing the power consumption of the system. To do this, we are researching on the parallelizing framework or programming framework of the program or software. So to realize a much easier parallel and distributed processing, and also utilizing the many kind of computer systems. And also we would like to optimize or reduce the power consumption of the system. And also, this is a very important thing that we have to apply these kind of techniques for the real application to contribute to the real society or cities. Okay, so do you think that today's computer system provides us enough performance? Do you think? No? Or yes? Do you think? So maybe today it's okay, but in the future we have autonomous driving, so we need to do that. And also we will have a kind of virtual reality. And also today we are very familiar with gaming AI. And also we have a big data problem. So when we think of the future, we still need much more performance from the computer system. To solve this problem, we are attacking the problem to how to parallelize the program. Parallel processing is a very important technique to realize a higher performance from the computer system because now we are facing the end of Moore's law, and it's very difficult to make it the single computer system faster, so we have to distribute the tasks inside the program among the processors, the process code, or something like that. So we have to do that. Okay. So we have to divide these tasks into the multiple or many number of processors and make it faster. So this is very important technique. But the problem about the automatic parallel processing is it's very difficult to parallelize the program. So we have to analyze the program and divide the many tasks. And also we have to think how to assign the tasks onto the processors. And also we have to think about the many kinds of systems, so these kind of laptops or smartphones or cloud systems. So we have many kinds of computer systems today, so we have to think all of them. So today, so in many cases, we have to do that by hand or human effort. That's very tough work, so we need a kind of automatic parallelization technique. Now, so we are researching on how to make it automatically, how to realize automatic parallelization. and we are developing the compiler to do that. Okay, so another issue about the computer system is the power consumption. So actually this session is for green technology, so we are talking about how to make the system green. So as you see, so today we have many computer systems behind our laptop or smartphone or something like that. We have, behind the internet, we have huge amount of computer systems, the data center, the supercomputer, something like that. So actually, so Google has a very big data center, so consuming more than 200 megawatts. And also the largest supercomputer in Japan, K-computer, is consuming around 12 megawatts. But when we think of the nuclear plant, one nuclear plant, so usually it generates the 30 or 40 megawatts. As you see, it's very huge amount of power it's consumed by the computer system. So we need to realize the technique to reduce the power. So, and also we should make it automatically, we should make it more easy way. This is automatic, maybe this is by the automatic parallelization. So based on this background, so I would like to utilize the parallel processing technique for the pre-computing. So the one idea is that by using parallel processing, we can make the program much more faster. So we can find a kind of chance to reduce the power consumption. So I'll talk about this kind of later. So and also, just reducing power consumption is not enough because the most important thing is the power efficiency of the system. Because just reducing power means sometimes means just reducing the performance of the system. So we don't want to reduce the performance. So while keeping or improving the performance, we would like to reduce the power consumption of the system. And finally, by utilizing these kind of techniques, we would like to contribute to the real society or real system, real social systems. And we believe that so we can make it by using automatic parallelization techniques. Now let me show you a basic idea to reduce the power consumption of the computer system. So one idea is execute the program at the maximum speed of the system, and then rest until the deadline, given deadline. So this is one case. And another case is that make it more slower, but while keeping the deadline of the task. So this is a very simple case, but this is a kind of very important strategy for to reduce the power consumption or the energy consumption of the system. And by using the compiler system, so compiler can analyze the program and how so we can the compiler can search the opportunity to do this kind of thing. So we can apply the compiler system to do that while parallelizing the program. Okay, so let me show you the kind of example. So this demo focuses on the performance itself by using the optical flow computation. Okay, so optical flow computation, oh, excuse me. Computation computes which part is moving in the figure and also the direction of the movement in the figure. So on the left, this is a sequential execution of the program, And also on the right, we can see the parallelized execution by using 12 cores. So by using parallel processing, we can make this program much faster. And also we can, so in this case, we achieve around more than 27 times speed up. So by utilizing this speed, so we can find the opportunity to reduce the power consumption. So when we can have the room until the deadline, so we can make the program more slower. And this means that we can make the energy consumption of the system much more good or lower. So in this case, we could achieve the 70% power reduction of by using the same application. So this is one case of just reducing the energy consumption or power consumption. And another thing is that how to utilize a given power budget. So when we think about the HPC systems, the given power budget is very limited. And in many cases, it's very hard to make full use of the given power budget. So this means that we cannot utilize the power provided for the system. So we are thinking of the hardware over provisioning technology. So that means that we can provide much more number of hardware resources for the system. And then by using software technology, we can cap the total amount of power consumption of the system. So by using this technique, we can utilize all of the power budget given for the system. So this is an example. So until now, so I have talked about how to reduce the power or how to make more efficient, how to make the computer system more efficient. And also, by utilizing these kind of technology, we can contribute for the real society by realizing the smarter cities. So the ICT system is a kind of infrastructure for our society or human systems. And so we need to realize a sustainable society by using ICT systems. So now we are attacking the real application to contribute the human society to realize by realizing the smarter cities. So now I'm showing the two examples. One is the earthquake simulation, and another one is the traffic control optimization. So by using the parallelizing technique, so we try to make the earthquake simulation faster. So in this case, in this simulation, we divide the real world into the many number of box cells and calculate how the power of the earthquake go through the land, inside the land. And then if we don't apply the parallel processing, we can get much slower execution performance. But when we get applied parallel processing, we can get much more performance than 100 times speed up, 100 times speed up. So this is very huge achievement, very good performance, but we need more effort to realize real-time earthquake simulation or to super real-time earthquake simulation. Because if we can realize a super real-time earthquake simulation, so before coming the earthquake, we can utilize the sensor data and calculate the earthquake situation, and then send the data to the people in the city, how to evacuate or something like that. So this is very important. work for the Human Society of Smarter Cities. And another example is the traffic system. So today we have many cars in the city, and we have to, if we can optimize the traffic flow, we can reduce the energy consumption of the city, and it's very important today's city. In this case, we utilize the dynamic programming methodology, so we can divide the situations of the traffic signal into the phases, and then we name each phases. And also we can apply the, by using this phasing technique, we can apply the dynamic programming technique. And then also we apply the algorithmic optimization for the optimization program. So we can achieve the much more better performance. If we don't apply the optimization, the complexity of the problem is exponential style, but after applying our technique, so the complexity is a kind of linear style, so it's very good performance. And finally, so this is a kind of big picture of my future research. And today we have many kinds of computer systems, PCs, smartphones, IoT devices, supercomputers, and cloud servers, and also maybe we can utilize quantum computers. And all of them are connected with the internet. And in near future, we should we have to make full use of these kind of computers, but all of them have their own functionalities and characteristics. So we have to think of which kind of program want to execute in these kind of systems, which kind of tasks should be assigned for which kind of system. So these kind of things have to be automated by our techniques, and this is our final goal. And then this kind of orchestrated or coordinated parallelization and optimization would make the computer system or human cities much more sustainable or efficient or very easy to use. This is our final goal. And we believe that that these kind of things can be realized combining many kind of techniques with parallel processing and our techniques. Okay, so today I talked about my research topic, parallel processing, and how to utilize the parallel processing technique for realizing the Greek computing, and how to utilize the parallel processing and Greek computing techniques for the more smarter city, realizing more smarter cities. Thank you very much.
We now jump to the last presentation, we presented by Noel Velázquez. This is not green technology. So. So probably we can use the time and have questions for the first two presenters and wait for the realization of this. So I don't know if there's any question for the first two presenters. No volunteers? Yeah, I have questions, yeah. So I have a question for you. I was just asking, thinking about how you deal with unstructured environments. So when you don't know a priori how the environment in which the robot is going to navigate, so yeah. How you deal with that?
Robot operation in competition, we will manipulate manual operation was applied. Autonomous operation and control is not so good for the competition states. Yeah. Now developing the autonomous control. Yeah.
It's difficult to predict what's going to happen if you don't know exactly.
Yeah.
There's many variations.
Yeah.
Difficult to deal with.
Yeah. Okay.
So how do you
That's right.
Preparing for that?
Yeah.
How are you preparing for that?
A simple case for slope and stairs, it is possible to autonomous control. But in competition, debris is very hard. Debris was setting. It is very difficult to use autonomous operating. Maybe in tomorrow's World Robot Summit, autonomous rescue robot is maybe known.
Very fragile, you can have another debris falling down.
Yeah.
So what's the way you will deal with that?
A lot of type of debris was setting. Almighty autonomical control method is not developed yet.
You have a question? Yeah. Here's a question for you.
Okay. My question is about machine learning. So I'm a computer science guy, so I would like to ask machine learning. So how long did it take for the learning about the door knobs or something? How long the learning? Yeah.
Maybe local case. Now is only one night.
One night. Oh. So then you achieve more than 99% accuracy. Yeah. I think that's very good. So you utilize a simple network, and then still you can get enough accuracy for the just in case. Okay. Thank you very much.
Sensors to detect light, or and how are you doing to succeed in this task to detect light?
high. And debris can be measured by using a 3D scanner. But measured, but never climbing that space automatically. Measuring is very high accuracy. And next step, we would like have to find the human. The finding human method is very, very difficult. Only the thermal camera, about, for example, the sunlight was from the window, and photospot was okay. And it is impossible to distinguish photospot and human. For example, using a CO2 sensor, but now development of CO2 sensor is very close to the mouse. About 5 centimeters, it is impossible to find the CO2. This is important to find how to human being. Okay.
Okay, so now we jump to the third presentation and we take the rest of the questions at the very end.
My name is José. My name is Noé Velázquez López, and I'm going to talk about a development of a farm robot that we are developing at Chapingo Autonomous University. I would like to start my presentation with this slide that shows Japanese reality versus Mexico reality. And I found this picture in the one in the left in a museum in Hokkaido where they show the history of mechanization. And they say here that in 1960s, there was the last time, or there was this decade, they finalized using animal force for agriculture. And Mexico is still a reality in most parts of the country, especially in the south part. And I know that because that picture was taken in my hometown, in my father's land. So, as this start, I'm going to talk about a little bit about my background. I was involved in this project in the development of a fully automatic transplanting system for greenhouse cultivation in Tokyo University of Agriculture from 2010 to 2013. And this robot consists of 2 vehicles mainly. The first one, the working vehicle, that this is the one in charge of doing the transplanting. And the other one, the control vehicle, is the one in charge of taking the robot to the field. And also it's in charge of the position, the control position, the positioning control of the robot. So we have a 2D positioning system developed using a laser rangefinder, which has a 1 millimeter precision in 100 meters. So it's very precise. And about this background, I finished my PhD degree in 2013 and then came back to Mexico. And in Mexico, until then, there was no development in farm robotics. So I started a little project with my students in a class project and in this topic. So there's 2 kinds of robots already. First generation of robot, which means that we can automate some already existing machines for agriculture, like these tractors, where you have to put energy, which is fuel, basically, fossil fuel, and then we have the farm robots, and you need an implement depending on what are you going to do. And also we need an operator for taking the tractor, in this case, to the field. And also we have, in the other side, we have the environmental, where we establish the crop, and also we need water, we need solar light, and we need oxygen and some other things. And so all this combined give us an increment in the yield of the core, of the products. And the second generation of farm robots is this one, and where we already took the energy, the fossil fuel, and we take the same energy as the crop, the solar energy. And then we power our robot with this energy, so we have in the same environment, we have the robot and we have the crop, and also we put some other like water or nutrients, and we can have the increase in the yield. But also the farmers here, or the people, is just an observant of this process. What is the idea of this process? as I mentioned before, is to use the same energy as the plants used to grow. So we power our robot with the sound light energy, but also the plants grow with, there is more light in the field. So we have the growing plants, the crops, it's growing fast, but also we have weeds in the field that is growing fast also because we have good conditions of light. So the robot can go inside the cultivation and maybe cut a little pieces of the wheat, and then these little pieces go to the soil, and then these residues with some organisms going back to the soil as organic matter, and then we can increase the yield. So with these ideas, we start developing this robot in 2014 in Chapingo Autonomous University. It was a basic robot because we have no funding at that time, and it should be as cheaper as it could be. So even the students had to buy the motors and everything. So we did some really easy calculation of how much load we can take, how much is the thrust for the engines to move, and then we start building it, as you can see here. We test some drivers because we have agricultural engineering, not electrical engineering or mechanical engineering, but we are agricultural engineering. So we start from basic things, how to turn on the motor, how to change the direction of the motor, how to increase velocity, and how to reduce velocity. And we came with this first prototype, and we decided to have a skid steer vehicle, which is very easy to control because we don't have direction, steer direction, as you can see, so it can turn very easily in the same axis. So until this point, we have at least it moved, and then we take it to the garden and the faculty, and it should turn faster because one side's velocity is slower than the other side. But as you can see, it's not enough power to move it. So from this first step, we have some recommendation as more efficient motors, reduce the size of the vehicle, improve mechanical design, and so on. Also, we're using the MPU and the IMU, as Professor said, in his robot for rescue. And we are very similar in the sensors, actually. So we came with the design of and construction of the version 2 of the robot, also with no funding, because in Mexico it's very difficult to convince people that we probably need this technology. And so we decided to design and construct and evaluate an autonomous vehicle for monitoring and agricultural work. And here's the design. And as a main thing here is that we put the motors in a head position, and then we transmit the power to the tires by a chain. And now we can go to the field, and we reconstruct everything again, and we have made some pieces especially for this robot. And this is the main control. We have, actually, these motors that you see there are from power wheel toy motors. But these are very good. They are 80-watt power wheel toys, and they have a reduction that allows you for torque, and so the robot is very powerful. And we're using Arduino because it's very cheap and very easy to get here. And the main thing we're using is a computer vision webcam that allows us for autonomous navigation. Here. Also, here's the algorithm. I will go further later on this navigation. And here's the second version test, first test. And now you can see it has no power issues. It can go very well turning in this kind of field. And so once we have developed this, now we can go to develop some mechanisms, some implements for agriculture and labor. The first thing we did, because it didn't cost money, is an application for following someone. We are not controlling the velocity of the robot. If the guy moves so quickly, then the robot will lose it. So now, right now, just following him with program velocities, but it's working quite well. And as I said, we're using the webcam of the computer for this task. Then, as I said, we came to the implements as a seedling computer vision system for disease detection in some cultivations that we're working right now, some spraying for pesticides, fungicides, application of alternative energies in the robot. And so here is the robot with some solar panel, and I have to say this is not the best way to have the solar powers in the robot because it's so small. You have to have a separate unit and then go to charge automatically. So we went to the field and we wanted to do some tests. And as you can see, it didn't work. As everybody was very worried because one of the students, especially the one that is going in front of the robot, you can see it's not traction because it's a rigid system. And we already have installed a seed layer machine in there, in the middle part. So you can see his worry face because he was working on his master thesis and then we have to do anything again. But this shows that we were doing something wrong. And we redesigned again everything. So we put suspension and we put 4-wheel drive in the robot. We start over again, and we start all over again with the circuits, and we came with this third prototype. And we also changed the tires. So this is agricultural tires, and this is special for agriculture. And of course, our pets over there. But as you can see, we don't have problems of turning now, and it's moving very well in the field. And that's why we wanted to make this. Took us 3 years to come to this part, especially in the mechanical design, until we came here. We also working in the model, mathematical model for controlling velocities of this robot. It's quite easy because this robot is considered rigid, and we don't have changes in mass position in the robot, as the one I previously showed you in my first slide. So this is the mathematical model for controlling this robot. Then we developed software to autonomously navigate between corn or between any cultivation. Actually, we are using a webcam, as I showed you before, and now you can see the suspension working very well. It's independent suspension in this robot, and also it's navigating autonomously between the rows of the cultivation. The main point here is that our vision system adapts to light condition automatically. So if the sun goes, it is cloudy, then the light conditions change, and then if the sun comes back again, the lights change again, but this system adapts automatically to this point. So we are very proud of this development here because otherwise we have to use, as Professor, a rangefinder laser that is very expensive. It's more than, I think, $5,000 or more, and this camera costs, I don't know, $100 or all this. And we also test for bad condition. At least maybe we can compete with you in the rescue robots. I don't know. You have to take it to see it, but I think it's very good at this kind, not flat slopes, and so it's working very well mechanically. This is the software we have developed, and this is actually a video took from the robot while it was navigating through the corn. You can see the red dot there. So it's calculating the center of the rows, and then if the dot is left or right, then it decides to go to the left or the right to correct its guidance automatically. I repeat, we are not controlling velocity at this point, but it's working very well, and it's autonomously guiding into the field. So with these things, we already can do many things as monitoring, fertilizing, or even harvesting in the field. And this system is working quite well. We also this is a multitasking robot, so we have designed some mechanisms. This was designed, but it didn't work well. It's for mechanical weight control. It was actually tested in the competition we participate in Germany this year. We have developed a fertilizing and seedling machine, and also an autonomous spraying system that is here. So if it goes autonomously, then it can spray some pesticides, fungicides autonomously. And well, we think with this system we can reduce the amount of pesticides or chemicals we're using in agriculture. We also developed this seedler and fertilizer machine, and that is using the same mechanism actually for fertilizing and putting seeds in the soil. This is a demonstration, but you can see that it's working very well. You can move the motors faster, and then it can put more or less fertilizers and seeds into the soil. And also we are working on a larger, actually we bought this commercial seedler for larger grains like maize or beans, but it didn't work, so we are redesigning this. I have one of my students working on that right now. And recently we are developing also a weed detection autonomous system for weed control. So we just started this last week. It's our first test. You can see that it detects the plant and then sprays something on that. We're still working on the control, but it detects the plant with the same vision system, which also goes to the system was very cheap actually. So this is what we are working on right now. We also did a test that while working, while the robot is moving, and it should do something like this. It will go moving, and then it will detect the weed. Then we move the sprayer, and then we'll apply some chemical from herbicide. And right now we are working on 2 more versions because a company, a Mexican company, came 1 month ago, and they want to build a larger version of this robot for orange and lemon. So we're designing a larger robot for them, and they want to build it by the end of the year. And also they want a smaller version of this robot with the same platform. Also we are using the same sensors as Professor for the completion of this robot. So as a conclusion, a robust multitasking platform for agriculture has been developed. The development algorithm is very robust, I said, in light conditions. It automatically adjusts for these lights. And also this allows for autonomous navigation in the robot. And a cheap solution for autonomous navigation was developed. This is the first point we have done. And we are developing some implements and other for development at this point. So thank you very much.
Thank you. Now we come back to questions, if there are questions from any of the participants. Questions? I have questions for you. So, in terms of power consumption, you show some examples when you use more than 1 core for. So, what I didn't see how you relate the 1 core power consumption with the multi-core power consumption for doing the same task, because that would be a fair comparison in terms of power consumption, not only in terms of speed.
So your question is about why we can reduce the power consumption, energy consumption,
because you show using the algorithms how to optimize, but when you didn't show doing the same task with just 1 processor, how was the power consumption when you jumped to 12 processors?
Okay, so the power consumption of the processor is come from the frequency of the processor and also voltage of the processor. And the power consumption is depends on the frequency and doubles of the voltage. So when we can slowen the processor, this means reducing the frequency. So we can also reduce the voltage of the processor. So maybe this sometimes we can say that this is a cube of the frequency. So when we 2 times slower, so we can use the power around 8 times smaller power consumption or energy consumption. So this is the main reason why we can reduce the power consumption.
I have another question now. Does you have a question there? Yes, please go.
Hello, I'm Francisco from the Mexican Association of Former Scholars of Japan. My question is for Noé. From the last time I saw the beginning of this project, well, I can see that you have developed more prototypes. I would like to address the question that what would be the comparative of this type of technology that is going to be implemented. I can see a lot of advantages, and I would like to know if you have already identified which other less robust machinery or technology can be replaced with this technology, and if you are also willing to do studies on the energy saving, on the water saving, and the other materials and resources savings with implementing this type of technology.
Thank you for the question. Yes, of course, we are doing right now the research of how to, because this is electrical robot, so we have to have energy source, and we are thinking that it probably will be sunlight or photovoltaic source, but also we are thinking of doing some research on wind energy. This has to go at the same time we are developing this prototype. And we are also having or hoping that somebody in Japan maybe invent some battery that lasts 3 or 4 days, and then we don't have to worry about that. But until that time comes, we are doing some research on how to charge autonomously the robot. As for as the main idea for this design is to make it as cheap as possible, so we are using materials that can be get or could be get here in Mexico, and most of them you can buy it anywhere in Mexico. So if it gets broke, maybe it can be repaired easily. And also the software, we are using software, free open source software as OpenCV and ROS, and that will help us for more wide range in using this robot. I didn't get the first question.
You already identified technologies, machineries that can be replaced with this type of technology.
Yes, this robot is not intended for replacing tractors because they are much bigger, powerful. This robot is intended, in the case of Mexico, is for harmful activities such as doing pesticides or chemical applications, because in Mexico, unfortunately, the people who do that, they don't protect themselves. So they are even sometimes naked and applying the chemicals, and we are thinking that this is a solution for them. And also, we are thinking that we can help, because in Mexico, at least this year and last year, we have a heat wave that the recommendation were that you have just 30 minutes outside, but farmers are all day outside. So we are thinking these machines could do the job for them.
Hello, my name is Eugene, and I think it's a very good beginning, but it seems to me that a real tractor, agricultural tractor, is easier to control than this, because you just have to control the speed of the engine, also the transmission, and because this is okay, but we need to think more to the real situation. And of course, it's more expensive, but I think in Chapingo you have good tractors, and somebody has to start to work with real tractors, I think.
The reason why we start with this small robot, because we don't have funding, of course, But I think that the technology that is being developed for this robot could be easily applied to a tractor in the future. We can do the same thing as I explained in the first slides. We can automate a tractor, or we can do differently in this. And the point of this is that we use the same energy as the plant.
Any other question?
Good evening. Thanks a lot for your presentations. They were impressive. My question seems pretty obvious, but I would like to know your professional point of view. Which is the social impact of your robots?
For the two of you.
Well, as for this robot, I think I just mentioned, because the social characteristics of Mexican farmers are that they do a very heavy job and very harmful job, as they are working as applying chemicals to the plants, and unfortunately for us, they don't protect themselves. So I have the experience that just 1 month ago, one farmer came to Chapingo and said, I want the robot right now because my people that they don't protect themselves, and then probably they will get sick in the future. So I don't want them to get sick, and I want them, I prefer them to use this robot rather than them to get sick. So for us, I think it's for helping them to these harmful activities in the field, and also if you want to see economically, we are pretending that using this robot, the materials you are using in agriculture would reduce, and therefore your profit will increase.
So about the robot, so for the computer system guys, so the robot is a kind of very good interfaces between the computer system and the real world. And so I think that we can find many interesting applications for the real world from the computer system. And also we have to think about how to interact. Maybe in the previous session, with Amauka said, so we have to think about how to collaborate or interact with the real world. So this is a very interesting application for the computer science field also.
We're running out of time, so you have more questions, please ask them after the session. So I want just to give you a certificate for participation. So this is for you. This is for you. Finally, this is for you. So thanks very much for attending the session, and bye-bye.